Okay, so welcome to the talk about if you like it, when you should put a test on it. I'm Chris. I'm working for QuantLab, which is a high-frequency training company. And today I will be talking about testing. However, the talk is not about good practices with testing. It's more about how to develop a testing framework using modern C++. And we'll try to learn some C++20 whilst doing that. The idea is that the talk will be split into 3 parts. So we'll start from the motivation, why we would do that, what modern C++ can give us in order to make testing frameworks much better, and what problems we have with them at the moment. After that, we'll go to the implementation of it from scratch using C++20. It will be a simplified implementation, and we can see how powerful C++20 is, because we can do it in 200 lines of code and make quite a few features. And after that, hopefully we'll achieve that goal. We'll see how we can, evolve that envelope in 2,000 lines of code and present UT, which is a unit testing framework, which I worked for quite a while right now, which has way more features and is more powerful than our simple implementation, but it leverages the same kind of approach towards testing. And briefly, we'll take a look into benchmarks. There are mainly compile time benchmarks, because that's what is important about benchmarking testing, but also the runtime will be shown as well. And after that, we'll just do the summary. So I hope that sounds good for you guys. If you have any questions, just put it on the chat. I'll try to make some breaks. The talk is quite long, so hopefully I don't bore you too much. We can skip some parts if necessary. Just a disclaimer, if there's a dark blue background, that'll be something to remember. It'll be probably some C++20 feature or a good practice, which is important to remember from the talk, if anything. And the green background will mean that we achieved something, basically the goals which we try to set up. So without further ado, let's start. So the motivation. The basic motivation is just to be able to easily test things without hassle. And I believe that C++ is not the best language to do so from the beginning. Like, we don't have much facilities to do so. So for example, how we would do that with the C++ standard features? I don't know. We would have a main, probably a comment or something, and an assert, which is not ideal. That only works in the debug mode. In the release mode, that would go away. You wouldn't even see the result. And there are a few problems with that. So I kind of specify a few of them here. We cannot list or run specific tests. It was just a comment, so we cannot do anything about that. There's no useful information when the test failed from the assert. No why, no line, nothing much. It will be hard to scale, integrate, debug. It only works in debug, doesn't work in release. More tests, all of that would be hard. It will be easy to make mistakes because of the, for example, implicit conversions and other things which framework, so to speak, won't give us. It will be hard to follow good practices like TDD or BDD because we don't have facilities to provide Gherkin style interface or different approaches. And there are obviously other things. It's kind of a generic list, but you get the gist, I guess. So that's why we have frameworks, and there are libraries. There are a lot of them. I have to mention. A lot of them are really good. So there's a Google test. There's a Boost test, Catch, very popular recently, Dog test, and there are others. All of them have pros and cons. I will focus on the problems because I'm going to claim that we can do better with the C++20. So to prove that point, I have to kind of do that. So what are the problems with the current solutions, current frameworks? They're macro-based. I consider that a problem because I believe it's way better to have a framework which is not macro-based. I feel like macros are the evil. You don't want to get into them. And if you have ability to implement primitives using C++20, and then if you really want, you can get the macros out of them, then I think it's a much better approach. And it also, you have issues with the line numbers, you have issues with compilation times, error messages, everything is quite difficult with macros. And I feel like C++ and modern languages just want to get rid of them. So far we couldn't because of the file and line, but with the C++20 feature source location, we can actually do that. So we'll take a look into that. There's a lot of boilerplate you have to do in order to do all those, use some of these frameworks. Some of them are slow to compile. Some of them are hard to integrate because of the libraries CMakes and all those things. Obviously that's generalized. I'm not specifying that all these frameworks have the same problems or any of those problems, but that's mainly the problems with the current frameworks. So what's the future? We can do C++20 macro-free framework, which we'll see, with the minimal boilerplate, minimal learning curve, easy integration, flexible, scalable. Yeah, that's just fancy words, but we'll see, maybe, hopefully we'll see why that's the case. So the goal here is to get this sum easily tested. The first goal will be to make that code happen. As you see, it's just 7 lines of code. When we have the module, we have the test, we have the comparison, which is guaranteed by the expression here to be not failing on the conversions as well, failing if there is a implicit conversion, and it allows you to list the tests, run specific tests, and everything like that. And it also, what is the most important, shows the line number and why it failed. So that's the main goal of this talk. The second goal is to also do the test suite with it. And the follow-up will be just to see what we can do in, like this part will be in 200 lines of code. And the follow-up will be to show use cases and what can be done in 2000 lines of code with the UT framework. So I hope that sounds good. So let's get to the implementation. As I pointed out, it will be C++20. So if you're not familiar, I hope I will explain a few features. I won't be going into much details, but hopefully it will be clear. I'll go a bit fast because I have a lot of slides and a lot of things to share. But feel free to slow me down if I'm going way over. I just want to be in time, and probably longer than I expected either way. So let's just try to start with the UT module. So how to make this line to compile, import UT. We can implement it by simply starting with the UT HPP. Modules can be in any file. HPP is just a simple approach because it allows us to have the single module or single header library combined. So that's why it's chosen as HPP. So we start with the module interface unit, which I have to apologize. Modules are quite not that intuitive if it comes to syntax. But here we just say export module UT, which means that we have the module UT as an interface unit. After that, we'll import std, which is the standard template library, because we'll need to use some of the facilities of the standard, like index sequence or anything like that. And after that, we'll export namespace. We will just, do it a simple way by exporting the full UT v1 namespace so that everything will be available. Modules allow us to export just the specific things, but just for the simplicity of the stock and the, to analyze of code, we'll just do that. So if you have the main CP following that, which will just import it and has the main, we can easily compile that by using Clang in that case with the emit module interface. We'll create the PCM file, which is the precompiled module, and we can link it with the main CP as well, and that will provide us the main binary, which we can just run without an output, but it already allows us to do the first line, which is the import. So I hope that makes sense. So moving on about the modules. So as I pointed out, a module interface unit is a module which starts with the export, and you can read about modules way more into the draft. As you probably noticed, it's also the blue background, so there's something to remember about the modules, that they will be coming this ++20, and they promise quite a bit. The technology is kind of similar to precompiled headers. However, you can hide a lot of your implementation into the module. You don't have to expose everything like precompiled headers do, but they offer much faster compilation times as well because of the translation across the translation units. You don't have to, parse the include files multiple times. That's the main gain. Modules, however, won't speed up a compilation of templates. If you have a lot of instantiations, they have to be instantiated either way. That depends on the point of instantiation, not of the module. Although there is work for the precompiled header, for example, in Clang 11 to allow to instantiate them. But you have to know the types as well, which you want to instantiate the module, the templates with. So if you know that, you can always improve your compilation times with templates. But if you don't, that always will be done at the point of instantiation. But that's the modules. Modules are great. Modules are coming. They are accepted. They're in the C++20, and you can read about it in the module draft. So hybrid module already started, which is already an achievement on its own, in my opinion. We can start with the second part of it. Second part of the test is just to have this underscore test and test itself working. So the idea here is that we have the sum, which is the name of the test, underscore test is the UDL, which will allow us to implement behavior following with the lambda. So we'll try to implement that with the concepts in order to avoid substitution failure is not an error tricks, and just have a clean design with the C++20. So concept C++20 features as well, and they allow us to do constraint to apply constraints on types. So here is a simple test concept, which will have this requires clause, and will require the following: the test name. Yeah, we want to have the name of the test. So in the above example on the slide before, there'll be the sum, and that'll be required to print the running. In the motivation slide, there was a running name, which allows us to do that, and that was part is required by this concept. This name has to be printable, and the printable means that we can just outstream it. And here we have a printable concept which requires outstream and the type, and just cout it to the EOS. We also want to be able to assign, as you see here on the right side, the test equals a lambda. This framework is lambda based. You probably noticed that already, but you'll see that across the talk that lambdas will be used quite often, because that's where the power of C++ actually comes, and the functional programming. So here we just require the assignment, and the assignment is just void because we don't want to execute that. So that's the UT test concept. just to, give you a heads up about the concept. Yet another thing to remember, the second one. I promise there will be less because we just have to start with some less things to remember. We just have to start with things in the beginning to be able to move on.
I have just a quick question.
Yeah, go on.
On the concept, could you go back to that? And maybe I missed this, but it reads like you're requiring it to be a lambda that is convertible to a function pointer, so it has to be a captureless lambda, or am I reading that wrong?
Yeah, that's the fair question. It's just no, it's not required. That's the short answer.
Okay.
It's just the concept is not fully complete for your case because
Okay.
It's a simplified framework. So the version in 2000 line of code will have lambdas with capture as a requirement, but this one doesn't. It's just for the simplicity of the talk.
Oh, okay. All right. Thank you very much.
No, it's a good question. Thank you. So yeah, moving back to concepts. There are concepts in draft, not in the draft, in actually the language for C++20. You can use them already in the newest compilers. So as I pointed out, there are type constraints. They kind of like act like documentation for interfaces, or like, when you have abstract classes and the virtual methods. You can also do the same, not the same, but similar things with the types, which were lacking. And the main problem why the concepts were introduced was that the compilation errors were coming from the libraries where they were used, not where they were instantiated. And concepts allows us to do the early check-in, and if it's not satisfied, just to bail out. So we get better error messages because of that. And we also get better compilation times because it's a language feature, not a language hack as Sphina, for example. So concepts are good, concepts are great. Really encourage you to use them if you can. So you can also consider true a concept which is like the auto. Auto is like the least constraint concept, which is applied by default, right? When you pass auto as a parameter to lambda, you can consider that being a concept, which is the weakest one and just doesn't have any constraint. So you can do something like that when you have a foo function. That's a terse syntax. That can be done many different ways. I won't be going into details with the requires clause, expression and stuff like that. But the terse syntax is just prefixed before the parameter. So we have the foo, which takes the anything as a template, and this auto means that we require the least constraint concept, which is basically everything. So that's similar to full auto in that case. You can also have auto false, and then you can't pass anything to that function because nothing will satisfy false, because concepts are just predicates. Okay, so we have that. Let's just try to write an implementation for the test then. We have this name, that was one of the requirements. Let's do the string view. C++ 2017, I guess, a feature. And then this operator equal, which is passing the invocable, which is the test. That's where the question was coming from JSON about what we can pass. We can pass anything invocable, but the test itself will only satisfy something which is convertible to the function pointer. And here we just log running the name because of the simplified framework, and we'll just run it. In the bigger version, we would obviously store the name and run it later. But for the simplified, we'll just do that. And then we'll use UDLs, which is the user-defined literals feature from C++17 to create the test in a reasonable fashion with quotes, and after that underscore test, which is the main idea about the framework. You can also find the kind of odd syntax for concepts, like concept test auto. That's still the terse syntax. Wherever you have a parameter or return type, you can put the concept before. which means that it has to be satisfied. So this function won't be able to be called unless the return type will satisfy the test concept. And we just create the test with the name and size for the string view. So having that, we can write the code as follows. Sum underscore test equals lambda. And we'll get the running sum as a result. So we're getting close to our first goal, to be able to have an expectation. We have the test. That's the first part. But that's not the most important part, because testing is about having, tests, and especially having an asserts. So asserts would be the second part of it. So right now we would like to write the line 5, which means in that case, just to have the operator equal ability to compare expression and give us a failure in case they're not satisfied or not equal. Additionally, like Qt framework also, and maybe if you have time, we'll get into that. There is like expect functionality as well. So instead of just using the equal, you can use expect sum equals, which might be more visible, like more intuitive for some. But this one is the less boilerplate, right? And it gives you everything you need, in my opinion. So here we compare 3 to 42, as pointed out. However, with the operator overloading, we have a few issues. The main one basically is the fact that you cannot overload the built-in types just by default. You can read about it in the standard. So what does mean is that we cannot do operator equals and end. That won't work. That will give us an error that the operator must have at least one parameter of class or enumeration type. So in order to achieve that, we can do something like operators equals with, for example, integral constant and end, and that will satisfy the standard and the compiler. So something to remember, that we cannot overload built-in types, unfortunately. That could be powerful, but you can see the reasons why that's prohibited at the moment. So let's just try to write it. So in that case, we'll write an operator equal, which will take left-hand side and right-hand side, and will require an operator concept, at least for one of them. And that concept requires the LHS and HS, which are just the side operators members. And after that, the idea is that the operator has to be convertible to a bool, and it has to be printable because we want to print the expression itself. And then for the operator equal, we just return an equal kind of object which will satisfy these concepts. So how to implement that one? It will be just it will be just a struct, and on the bottom you have ctats, which is template class deduction guide for it, so that we can easily pass it without the propagating angle brackets around. Not really important. We'll have two members, and in the destructor we'll just call if this expression is not satisfied, we'll call the error. Why we have to do that in the destructor is because of the equals operator creates a class which will die at some point, and then we'll check the result. It's like mocking basically, which does a similar thing. If you use expect or assert, something like that, we can do it differently. But with the equal, we will have to do with the just equal operator. Without the function, we'll have to do it in the destructor. And additionally, we provide this operator bool for comparing both sides, and the streaming operator for both of them. As you probably noticed, there's an error here and a get. That's the details and the implementation for them is quite simple. Error, just print an error and the expression. The expression will be printed accordingly to its stream operator. And the get will just verify whether you have a getter. If you have a getter, the value will be get from there. Otherwise, you'll just return the value. It's important because sometimes you don't want to convert from the things you have, and the value will be required there to be get. And this pattern is quite often used. One of the last things to remember, which is called design by introspection, popularized by Andrei Alexandrescu in the language. And the pattern is quite powerful and simple. It requires you to use if const expr, C++17 feature, and the requires clause with concepts. And what does mean here that if the t, which is passed to a function, has a member foo, then we'll go to the first branch and we can call t.foo. You can imagine if you do this if without const expr, that will just fail to compile, and requires it's a handy way to do that in place without writing named concepts. Otherwise, we'll return 0. So if you propagate a struct which has the foo, we get 42. If you propagate a struct bar which doesn't have the foo, we'll just get 0. So you can read way more and listen to Andrei about it. It's super powerful tool to have in your hand if you can use it. It speeds up development of a lot of things and makes a lot of things very simple. So yeah, something to remember. So right now we have this assertion. We can write this code. However, we don't have this _I at the moment. So let's just define user-defined literal, which is this version. I think is from C++17. You could do that with C++14, but it wasn't C++11, but it wasn't with the char ... which allows you to parse the whole string as characters and produce compile time constant. So we can do that with this handy trick with the lambda, which is invocable on its own immediately. And you can see this make index sequence will produce a call for the lambda, and C++20 feature for the passing the auto ... allows us to do that easily with the index sequence. And then we'll just return the integral constant with the calculation for the number. So in principle, that will just return integral constant on an end with the value here of whatever that char ... expand to. So for example, if you static assert 0, we'll get 0, 42 _ I will give us 42. So this pattern is quite common and quite handy in C++20. It's called like invoked function expression, immediately invoked function expression, which you could see, and that's the idea about it, behind it, that we make the index sequence. When we have the lambda, we expand that lambda, and then we can return using the fold expressions C++17 feature with ... So if you have anything like these lambdas, we can just call this variable template and get the result out of it. So having that, we can get this assertion to compile. However, there's a bit of problem with it because it uses this error function. However, it printed the 3 equals 42, which we wanted. It's from equal, and it printed running sum, which is already an achievement. However, it's missing file and line because we don't have it yet. And in order to do that, we use the C++20 feature source location. Source location is a a new feature which will allow us to remove macros from frameworks and login, for example, because it has the information about it. We don't have to use the _ file _ line to get the line, column, file, or a function. That's the interface of it. You can read it in the standard about it. But it has some problems as well, especially if the operator == not the source location. However, the operator == is kind of limited because it cannot have a default argument. So it's really important to have the source locations on the point of the instantiation, because otherwise you will get the source location of your implementation, which we'll see in the second, which is not ideal either. So since we cannot do that for our operator, one approach would be to implement the equal, re-implement it with the location, right? We pass the members, the expression, and after that we pass the source location of the current. However, you will see, and it's kind of a hint here, the file and line would be UTHPP and the line instead of what we actually desire, which is the callee site. And if you change the error to pass the location, we can get the file name and the line, and we'll just pass the location, which is from the equal operator itself. So what will happen if you do that with the sum? We'll actually get UTHPP 128 failed, which is not exactly what we wanted, because we wanted the main CPP line 5 instead, right? What you did, UTHPP 128 doesn't give us anything for that use case. So that's kind of annoying, but we can work around that. As I pointed out, value location is not value location. The source location has to be part of the instantiation to be properly propagated. So we can introduce this. There's a question? Or no? Okay, so
there's a question in the chat.
Sorry, I don't follow the chat. I don't. Okay, can anyone express that?
So someone asked if we have two asserts and one of them need to abort early. For example, if you have a not pointer test in the first assert and the second dereference, what should you do? Do you support that?
If you want to the reference after the first sum. Yeah, so yeah, we won't cover that in this simple UT framework, but the proper UT framework, and we will see how that works, allows to have fatal assertions. So it means if the expression, for example, equals or sum will fail, you won't go further, and you will just bail out as you would do in like Google test. It's basically equivalent to assert equal, and after that followed by expect equal. So you can imagine like assert equal and then expect equal. We'll actually cover that in the example further on, if that answers the question. I hope it does, because I don't have the chat here.
Nice.
Okay, cool. Thank you for that. So as pointed out, the source location doesn't give us the point of instantiation the right way. However, we can kind of work around it by having a type, like a value member type, which will propagate the value and the source location with it, and just some getters for it. And usage will be a bit different. So our equal operator will look a bit differently. So we'll have this value location here as a part of the operator equal, and that will be used by C++ to instantiate that class in the particular moment when you do the operator equal. And the left-hand side will have to match the right-hand side of the type, which is the value type, like end and end. And if you do that, that will allow us to get the source location of the callee side, not not from the inside of the framework itself. You can also see on the first line here that we can, instead of class or type name, we can use an operator as a concept as well. That's yet another way of doing it, just to confuse everyone who is not using concept. But on top of that, we have to propagate error with the location. And here the left-hand side has the location. So we can just propagate it and just have an anonymous struct which inherits from the base equal and overrides the destructor with if it's not equal, meaning error, and we propagate the location. So when that happens, and we go back to our operator equal, we'll get the test.cpp. That's the file which was compiled with line 5 failed, which is exactly what we wanted. So yeah, we can clap ourselves. It's achievement unlocked for the first goal. So moving forward, what about the second goal, the suite itself? If you want to write these guys, that's super simple with all the tools which you have already. So the idea about test suites is to have a lot of different tests in kind of combined way so that we can easily think about them and don't have like a huge main with all the tests. Instead of that, we'll have separate test suites which test specific things like assume, for example. So in order to do that, we'll introduce a suite which in the constructor will pass the suite concept and will just execute the lambda itself, and the suite is just an invocable. The idea here is the fact that since all of those tests are the lambdas as well, they'll be executed when we assign them. So if we execute the sum when we produce the suite, we can execute all those tests as well. So that's the simple way of doing that. And since it's kind of a variable, it's a global thing, it will be executed before the main. That's not exactly the way UT would, like the main UT works, but however, that's the idea behind this very simple framework in 200 lines of code. So suite is done. We run it with the suite, and we get running all the tests as expected. Very simple. Yet another achievement unlock, which was the second goal. So we're going really good so far. So maybe we'll have some time for the bonus features before we'll move on to the framework itself. Maybe you can just do expect, BDD, spec, and compilation times. I'll just go really quick right now, quicker than I was going so far, probably which is too quick either way, but just bear in mind with me if you can. So as I pointed out, you don't have to do like equals equals. You can do expect. It's a bit more boilerplate, but also allows you to do other things like streaming. You could also stream the previous solutions. So you can imagine just the parents without the expect and the streaming part of it. That's supported as well. But expect it's desired by some because it gives you this ability to think it as a unit testing framework. So the expect is quite simple to implement because here is a function. So we have the location already because that will be the callee site. We have an expression. Expression is something which is convertible to bool and it's printable, nothing special here. And that will be the verification. We just do the error. It's basically the same as destructor, and we return the CR so that we can stream it. And then we have our operator equal as before, not the value location version. So if you do that with the code above, we get the main CPP line 4 with the streaming operator. So that was quite easy. BDD is even easier. BDD is basically approach towards, structure your test a bit better than just having expect assertions in the tests. And it's done by introducing given, when, and then. And here you can see given is just a test, which is a lambda. When is just the test, which is the lambda. Then is just a test, which is a lambda. Having that, we can write something like that. Given I have a sum, when I add 40 and 2, then I should get 42. So right now we combine the assertion that with the test syntax assertion and the expect. Doesn't really matter, we can do either. But you can see the test itself, it's quite easy to write and it's more expressive. We can also wrap it up with a underscore test on top of it if you want. And that's what will be printed. And we'll get the error on the right line and printed everything as well. So that's nice. Spec is from Ruby, quite popular. Maybe some of you are using it. It's basically the same as other frameworks. It's just using describe and it. It's the same as BDD. We just say describe and it. Just wrappers, aliases for the lambdas and the test. And when we can write describe a sum, it should add arguments. And that's it. And that will run it and will produce the what we actually want. It will also print the additional 8 arguments for the function call. And the last thing, which is the compilation times. As pointed out before, we can pass lambdas to the operator. Lambdas are guaranteed to be unique types, which is a bummer for the compilation times often, because unique types, unique template instantiations cannot be memoized, meaning slow compilation times. However, we can erase that by having a pointer. So the first use case would be for all the tests which have capture, as Jason asked before, or do not have capture. Sorry. If they have a capture, they'll be going to the first one. If they can be converted to a function pointer, they'll go to the second one. And that will be 5 times faster just to compile, because the type will be always the same. And we'll just store the pointer in the proper unit framework, but here we'll just run it. But the idea is that we won't propagate the uniqueness of lambdas into template instantiations further on. So if you look into the standard, the lambda expressions are unique, and that's part of it, which means that if you do a static assert on lambdas, they will be different. If you compare the types of them, they also will be different, which is a great way of getting a unique things or unique identifiers, and also a great way to hack meta counters and other stuff with the template metaprogramming, which maybe is not desired. So that's about the implementation. You can find the full implementation in that link, like the whole code, 2,200 lines of code. You can also check it online. If you follow the Godbolt, you can just click it for the header. So this implementation didn't show it, but it's a header or module. And you can find the module on the one box, because it's not possible on Godbolt to compile modules yet. But on one box you can do that. So if you're interested in how modules work, you can take a look into that one as well. So having that, I don't know, it's a good time for quick question, but I still have a lot of slides, so unfortunately I will have to go faster. But the idea here is the next part is to just show a use case of what can actually be done in 2,000 lines of code. So 200 was quite easy to implement a simple framework. It has pros, but it has a lot of downsides, as pointed out already. What we can do with 2,000 lines of code is something which we'll take a look right now. Okay. So just an overview. The framework, which is available on GitHub, as the link above show, it has no dependencies besides the STL. It's kind of supported in C++ 17 because the source location is implemented by the compilers, but it's not. The applications are limited, so I wouldn't count on it. It's fully C++ 20. It works with GC9, Clang 9, MSVC as well, with some caveats. It's a single header, single module, 2,000 lines of code. It's macro-free, which is the main thing. There's no macros there. And it has tons of features, which we'll take a look at some of them, like features which most frameworks have. As pointed out, limitations may apply to C++ 17 and MSVC. And it's also, you can find it in Boost namespace, but it's not official Boost library or anything like that. This is an extension which potentially may get in at some point. So the hello world will be similar to what we had before. You can either include it or import. You have a main, you have hello world, you compile it, and you have, nice output. So the output is from the framework itself. It has colors, which is quite fancy, and also has the values for the asserts and tests and all the goodies, so that it can be followed easily. You can also filter the tests easily. You just have a config for you just override the config with the filter. You can imagine that you have utmain or something like that, which pass the first argument, which would be regex for what kind of test should be run. So if you have the main and you have different tests, you can easily pass them by, wildcard, all the tests, single wildcard, just one test, many equal. That is used to distinguish the subsection, and you'll get one test as well. So, nothing special. All the frameworks allow that, and UT as well. You can also tag things. So imagine you have performance test or nightly test, or you want to skip test. You can just put a tag on it, tag nightly, tag slow, or you can skip the test by having a pre-compiled tag, which is called skip, and this test won't fire. And you can override the tag by config override. So you can imagine you can pass it from the command line and say which tags you want to run, or you can use environment variable like Google test or something like that. And one test skipped here because we didn't run it, and the other one was run. We have assertions. We have different ways of doing that. There's a test syntax, and colors here as well important. That's what we implemented before. You can do expect with 1 equals 2, so you don't have to do the UDL part with underscore I underscore double or something like that. It's called mattress syntax. You can also use the UDLs. That's kind of referring to the previous question, the fatal assertions. So if you have something which you don't want to follow, so imagine you have a vector which has 3 elements and you expect 4, and you wouldn't like to crash on line 3. Then you can say that's a fatal assertion, and the fatal assertion might be in the compound statement as well, which we'll maybe see. And this way, the line 3 won't be executed because we will bail out on line 2. You can also have compound statements and use the floating point comparisons as well. And the precision here is based on how many zeros you put under the underscore d, for example, or the highest value of things after the dot, in a sense, because we know how many things are there because we parse them. So, for example, here the precision will be accordingly to that. And you can see that the compound statement will have colors as well. So the first expression is okay because the precision is just 1 decimal point, and the other one, which is taken from 1 0, like 2 decimal points. So up to 1 0 is okay, and that's near match. And we can also compare string views and other things. You can also pass the precision directly if you want to the comparison to the creation of the underscore d. There's login. So as I pointed out, you can log the expression, and that will print should equal. You can do that with expect as well. Nothing special here. You can log. So that's often used by some to log things whilst you're doing testing, just to understand where you are. There are sections. So you can imagine that you have a vector test in which you would like to test whether something is happening with it. So you have a vector, you initialize it with 5 elements, and after that you have this fatal assertion for the it being 5 elements. And here's a section which is called should resize bigger. We propagate this v. We can mutate it. So by default, lambdas are immutable. So if you want to mutate, you will pass, you will use the mute, like in Rust, to resize. But in the other case, you don't have to mutate the v because for the size, it's not required. So this expect will verify the size after resizing. And you can imagine here that since it's another lambda, the vector will be always created from scratch for that test. So if you go to the second test, the first test won't influence the second one. It will go from the beginning, which is the main thing behind the sections. So you have the vector, it will be created again. The first expect will happen. After that, the should won't happen. The expect will happen again. And we call this resize smaller when we mutate, and we verify the size again.
Is that mute a const cast?
Yes, basically const cast, yeah. So it's only valid if the certain circumstances are met.
Okay, okay. Because yeah, I've noticed more and more that Clang is optimizing around those certain circumstances. So it might be becoming more and more unallowed, if you will.
Well,
So you know.
right, but it's like it's guaranteed by the standard that if you have something, you can always cast, right? Unless it's non const, right?
But that's a capture by value. So okay, I accept your argument.
All right, awesome. So we can also have suites, which is great because we implemented them already. So for example, errors, it's a common suite which we can have for our use cases. And then you can throw and verify whether your callee site throws. You pass the lambda, which you throw, and you expect that it will throw as you would expect. You can verify also the type of the exception and the value if you want. There's no example here, unfortunately, but you could do that. You can also do this hacky thing on Linux, verifying an assert. Where that's a good idea or bad idea is debatable. However, it's possible with the forking of the code in Linux and do it. Like, it's possible in Windows as well, but it's not supported at the moment. But in Linux, you can do that. So you can verify whether the assert actually triggers anything. I wouldn't advise that though. you probably would like to redefine assert or something like that, or use boost assert, which allows you to redefine the handler and throw an exception, for example, instead. If you care about the performance, then in the production code, that will go away. In the test code, you would redefine the handler to throw and verify that it throws instead of trying to verify that the assert happened. So if you run that, we get 2 asserts into tests as expected. We can also have parameterized tests, which is pretty cool in my opinion, because you can go quite easily by doing it with the for. It's like if you want to do parameterized test in Google Test, good luck with that, and especially with the templates and instantiations. There are tons of macros to do it. I can't never do it. You have to use also do using and stuff. And since they are macros, you don't even know what they are. So it's a mess. Here, you can just specify the test with the for loop. And that will be executed if desired. You can also do it with the lambda and a bit different syntax for the test with the underscore test. You can compare types as well in that case. And you can just pass the tuple with all the types with the piping operator, and you will get asserts as expected. So both of those cases are very similar. You can do either. They achieve pretty much the same thing. The second syntax is more piping kind of way of doing it, and the first one is more imperative of achieving the same thing. You can also do test metaprogramming part of it. So if you have that in order to get the proper error messages, you require INTTP, which is non-doublet type parameters from C++20, which is currently supported only by GCC, but probably it's coming to Clang at some point. So you can say that this expression has to be constant, 42 underscore I equals I. You can do all the expressions which we did before with the test syntax. We just mark it as constant, which means that, oh, it has to compile. It's like static assert. However, the good part of it is the fact that it will give you a runtime check afterwards. So you will get the runtime error. You won't bail out in the middle of testing, which is not always desired because you sometimes want to, see whether other tests are passing or not. And you can verify the types, like type void equals type int. So that will fail that 42 equals 0 and void equals int. And it also will fail in case it will fail to compile if the constant is not constant as well. But if it is constant, then we'll give you a nice error message. Obviously, it will fail to compile if it's broken code, which is not compile time code, because you cannot pass anything with 2 angle brackets, which is runtime, at least at the moment. BDD is part of it as well, as you can imagine, because we implemented it in our simple framework. But there's a bit more. You can do a feature and scenario. I bet you can imagine how they were implemented. If you followed closely, it's just a lambda, which is the theme behind this talk and main principle why this framework works. It would be great to have, shorter version of writing lambdas without this boilerplate, but that's not possible at the moment. So we have to deal with this square brackets, but it's still better than angle brackets, I guess. So we can write the same test with the vector. When I resize, blah, blah, then expect. It's basically the same as before. We just use feature scenario given when then BDD style instead of the style which we used before. All this passed as desired. One new thing, which is part of UT, which we didn't implement, but it's super cool and super important for more integration style tests, which is the gherkin. I don't know whether you're familiar with the cucumber or gherkin, but the idea is that you write kind of in human way the tests. You say gherkin test, and you have a feature vector scenario, and given when then, it's like BDD. However, it's more towards managers, so that it's plain English, so that they can understand the product owners. You can write requirements using that syntax, and then that may go to the product owners. They can understand it. You don't have to implement it, but you have the code which actually will implement. You have the tests, the requirements, and then you can just implement the backend, which we'll do in a second, and get the test running. They can even be written by the product owners or stakeholders and given to you in that format. Then that's very powerful to separate the business logic and the implementation of the of it. Might be load from the file as well. So if you have a feature file, you can load these guys, and there might be a lot of them. Obviously, you can have a lot of scenarios, a lot of features, a lot of files. So what is the steps here? The steps is the gherkin steps, which is a lambda. You pass steps into it, and you can implement the feature. So with the BDD, we've seen it by, you had a feature which was the lambda. Here, you have a steps feature, which is also lambda. But the difference is that will be executed when we go through this code. So we'll parse it, parse the strings. Sorry, in the break. So we'll go and parse those strings here, and whilst doing that, we'll create the gherkin tables and things which are required for it to be run later on. So if you have the steps feature for the vector, we'll try to find the vector feature, and after that, scenario will match the wildcard, whatever that will be, so any scenario. And then we implement the given, which will introduce the scope. The scoping here is important, so you can see that the given, when, and then are scoped inside, because we want to use actually the vector which is from the previous scope. And here we propagate it not by value, like we don't capture by value, we capture by reference, because we want to use the same vector basically all the time, because in the expectation that then we need the same vector, so we don't want to copy it, because that's not executed as the previous test. That's a different kind of model of executing tests. We're going through the parsed code, not the lambdas themselves, which are executed when you kind of make them happen. I didn't mention, by the way, all those links are runnable. You can see on the top, you have always the link to the Godbolt. You can always click that. The slides are will be posted, and the slides are already available. You can click that link anytime you want, and it will go to the test, which will pass and show you, so you can experiment if you want. So if you run this one, we'll get all the tests passed as well. So there's one test, 2 asserts in that one, which I think is wrong. I don't know, because we have just one assert. Sorry about that. Anyway, the link will tell the truth. We can also do the spec, which we've seen already. There's nothing special about it. It's basically the same as before. But you can see that the scope here is introduced and we capture by value, because that's a different model than the previous one, because we want a copy of it. We want a copy of it because if we have another it, we want to reuse the same vector. You can if you desire, you can capture by reference, but you would have to understand that if you do that, the first test will potentially change the vector itself, underlying vector. So the second test, when it will be run, will have this side effect. And that's usually not what you want with the sections. Usually you want sections to be run from the beginning up to like the setup. That the setup, like if you think about the Google test, the first line when we start the lambda is the setup. So the vector is the setup. After that, you have the test, first test, second test, third test, which are using the setup. And after that, you will have the tear down at the bottom. So that will be the distractors from the vector. But if you capture by reference, the model and the propagation will be, you'll have the setup, the first test, the second test on the same vector, and the tear down. And that's probably not the desired model by default. By default, you would like to have the it be separated. That's basically a better practice. So yeah, we get these two asserts in one test. We can also do the parallel execution of the framework, which is quite handy if you have a lot of tests. And I just wanted to show how easily you can do it, because the framework, I claim that the framework is flexible. So for that, I will show something to show that. So this config, which we've seen before, might be overwritten globally for the parallel runner. The runner itself is something which allows you to override the printer, how the tests are run, basically everything. Everything is going through the runner and the printer. So if you want to experiment, you can always do that. But here, we'll just use C++ 17 parallel execution for each, just in order to execute test suites in parallel. Run is a function which is executed to run the tests, because all the tests are being stored, and after that, it's either run from the config, which executes them, or the distractor of the config if the run wasn't called explicitly. So in that case, the run will be called implicitly by the main being like the code being destroyed, the application being destroyed, and we can see that the execution will be of the test suites in parallel. So if you have the parallel one with tests and some other tests, if you run them multiple times, we'll get different execution orders of the suites. However, within the suite, the test will be executed in sequence. That's because they may have side effects, as pointed in the previous model kind of flow. So that might not be desired. So for this example, that hasn't been done. The idea here was just to show that you can easily override the runner, because there's a flexibility here to do it in parallel. We can also do simple benchmarking, and we can easily implement that by having a UDL for the benchmark, which just inherits from the test, and very simple one, just the clock from Chrono verifies how many nanoseconds the function, the test took, and you just utlog that one and print in the nanoseconds. So if you have a string creation benchmark, you do not optimize the creation of the string, and that's do not optimize, it just violates the cache. All the benchmark primos kind of do the same similar trick to invalidate the cache in order to not to get optimized away, and just verify the creation of it. And then you just get the time as well, and one test, no asserts here. You could imagine asserting that the string had hello, but as a simple showcase, string creation took quite a long actually. I think I ran it on Godbolt, so maybe not the fastest environment to do the benchmarking. And there's much more, but I don't want to bore you too much. I'm over the time already. You can, all of that you can find it on GitHub. The implementation, I will maybe show it. If you go to GitHub page, you'll find the documentation, tutorial, and everything required to start. It's the UT here, which you can find. It will have 3,000 lines of code and the module itself. So if you go back, I just wanted to show the last thing, I promise. Just the benchmark and the summary, and we're done here. So I did some benchmarks in order to compare the compilation times and the runtime of these frameworks: Boost Test, Google Test, Catch, Dog Test, and UT. I've chosen the newest versions back then. I try to be, it's really hard to compare the apples to apples with any benchmarking. And obviously, frameworks are so different and they require different flags to be passed. So I just compared the advertised versions of them being used. So for example, Boost Test is advertised as a static library the most. Google Test as well, as it doesn't have the header only. Catch is single header, although it's library right now as well, but it's still advertised as a single header. And there's like fast compile flag, which you can pass. Dog Test is single header, and it has super fast flag. I guess it's much better than the fast one. And UT is just without any flags. Because there are no flags to choose from. So the include itself, and I tested in Clang 9 and GC9. Catch 2 is quite slow to include, as you noticed, and Dog Test a bit not that fast, but rest is quite fast to include. And obviously Boost Test and Google Test is fast to include because of it being a library. So the includes are fast, but you pay for the libraries, but you pay once. So that's the benefit of the libraries. If you compare an assert itself, so one test, 1 million assert, one CP file, you could see that the common thing that compilation, Catch is quite slow to compile, rest is okay. Boost Test is quite slow to execute, and the binary size, Catch seems to produce the biggest. Obviously UT, it's all awesome in that benchmark. Well, maybe not obviously, but it is. So the test itself, that will be like 1,000 tests, just one CP file. You can see that Boost Test is not the fastest to compile. All frameworks seem to be slow on GCC release. It seems like the optimization are killing it. Execution, Boost Test seems to be really slow to execute. Rest seems to be okay. UT seems to be the fastest in that one. And the binary size, UT produces the lowest. The smaller one, Catch, seem to be having a big one. But regarding the binary size, you have to take into consideration that if you link it with the library, that will be a different thing. But if you don't, and if you include all the header file or a module, and those tests were, by the way, with the UT, with the header file. There is a test which compares header file and the module in a second. So if you have the suite with 10,000 tests and 100 CP files, so that would be like more from scratch tests with a lot of things to be tested. The compilation Boost Test seems to be the slowest, followed by Google Test and Catch. Execution, Catch seems to be slower right now. And execution maybe is not super important in testing because you don't care about the nanoseconds here, but you still care about milliseconds. And when the difference is here, like 2 seconds versus hundreds of milliseconds or tens of milliseconds in case of UT, well, it makes a difference in my opinion in the long term if you sum that up. So obviously you wanna compile fast and run fast because unit testing is all about the fast iteration, fast feedback. Binary size, I don't think you care much about it if it comes to the unit testing unless you have some limitations. But it's always good to have it smaller, right? Because maybe you copy it to a different server or whatever crazy environment one has. If you compare both, which means that we have a test suite and an assert, catch seems to be slow to compile and execute with post test. Kind of a similar follow-up to the previous one. And if you use the STL as well, so there will be like tests which are more involved with asserts. You see that UT and doc test actually got slower to compile because the STL takes most of the time. So includes actually take a lot of time to compile in comparison to the rest of it, which is quite funny. It kind of reminds me of the story of including regex. It adds like 10 seconds to your compilation unit just because you included it, although you haven't done anything with it. So it's kind of similar story when they're running the tests are so fast, including things might be really slow in comparison. And I think the most important benchmark is the incremental build because that's where you add all the time. You just change one thing, compile it, and run again. You don't change all the things unless you change the header, but it's often the case with testing that you iterate on test, iterate on implementation, depending on your implementation, whether you have CP files or not. That may change, but that's an important test. And you can see that doc test and UT are looking good here. Google test and boost test are a bit slower. Execution catch seems to be slow, but it also, keep in mind that the number of features which are exposed in catch is higher. So it's like I'm not claiming here that UT is the fastest, the best, or anything like that if it comes to any of those measurements. I just took some measurements and just sharing them and give you advice that always measure and verify whether that the case for you. And one last one interesting benchmark is headers versus precompiled headers versus modules. I put it out before that modules are implemented based on precompiled headers, so you can actually see that the results will be similar for both because we expose everything. Might be different if the UT framework didn't expose the whole namespace and just part of it, but that's not the case in the UT framework. It just exposes everything at the moment. So the compilation, you can see that the header is the slowest. The precompiled headers and the modules are pretty much the same. Execution, I wouldn't expect it to be different between any of those. And the binary size, it's very similar as well because all of that is the same code. So it's just the compilation, and you can see the compilation of the header is actually a bit slower. Not that much in case of 100 CVP files though. But it's around 250 seconds and 280 seconds, so 30 seconds gain might be a bit, I guess. So we gone through all of it. I hope you're still around because I don't see you. But just to sum up, C++20 is awesome. I hope I shown that by showing you the implementation. It enables a cleaner design and implementation of a lot of things, makes things much easier, and it's coming. Modules, concepts, source location are great, and a lot of tricks which you can do with lambdas and requires closer design by introspection. All of those goodies allow to really expressive and simple code and allow to write this framework without problems and much easier than I can imagine this framework with 19 wouldn't be possible. So great. So UT is an example of cutting-edge unit test framework. It's kind of used in production by a few companies already who are capable of using C++20. It's production ready as well, so and it's supported. It may get to boost at some point. Wouldn't count on that too much, but maybe. And it also exposes the primitives. So I didn't show, but you can find examples on the GitHub how to, for example, implement catch in UT. Because you can just put a macro on it. If you like it, then you should have put a macro on it. Maybe that should be another talk on top of that one, but yeah, maybe not. Anyway, you can implement different frameworks out of those primitives, which actually is stated here. So there's a potential of standardization, I guess. There are a lot of benefits of being able to just have primitives like expect or a test in the standard, in my opinion. Although you can argue there are pros and cons, whether they like, you can ship the STL with the tests, you can use them as documentation, you can use it as a leverage for teaching. You have a lot of capabilities here. It's unified. Everyone would use the same. You can see that in languages like D and others, which exposes unit testing. Everyone is doing the same thing with testing, not using 50 different libraries, which are hard to port. And you can easily build on top of that libraries which you want. And the assert itself is not the way, in my opinion. If you want to have tests being a first-class citizen. So yeah, thank you for sticking around if you did, and yeah, if you like it, then you should have put the test on it. The last thing to remember is like, it doesn't matter how good the framework is, you still have to write the test. If you don't write the test, doesn't matter which framework you use. So keep in mind and write your test first, preferably. And I'm open for questions or a happy hour if they are. Thank you.
And does any of it work? Like at work, I use MSVC and ReSharper, and I know for a fact that neither of those really supports concepts very well. MSVC compiles them, but ReSharper does not help warn about them. So how does tooling work, and how does, what's the support level currently?
Basic, I'd say. I'm VI guy, so I'm using VI. Just
so you're not used to any syntax.
So for me, I don't even use like I do have syntax highlighting, but I don't use like IntelliSense or anything like that. So in that regard, the same experience as before. Nothing has changed. It's just code edition for me on Linux. Compilers, they have bugs. Unfortunately, ICs are quite often, especially with concepts in Clang. GCC is even worse. Like GCC 10 is totally broken for a lot of use cases. So yeah, not great yet, I'd say.
Okay.
Modules seem to work quite well for me in Clang. Not
they've
as
had
well
them for a while, right?
Yeah. Maybe they work well because they're based on precompiled headers, so they had that implementation. I tried MSVC with modules. It did compile, didn't work. I gave up. I'm not a Windows guy. Just too much effort.
The MSVC conformance page says they only have partial support for modules currently, so they're not even done with them. they've had modules, but they were Microsoft modules for years,
Right.
but they're not conformant yet.
Yeah. And and module syntax is so weird sometimes. Like I don't want to show it, but it's like you have to write sometimes export import std if you import it and you want to export, which is like requires with concepts, or no except, and so on. Yeah. But private sections with modules, module syntax is a bit weird, but yeah, it's still better than. I still love modules for the reason that you can hide the implementation of some things. Like encapsulation is much better.
Yeah. Cool.
So Kris, I'm working on my talk for CPPCon, and I've still got your examples using this framework in it. And
yeah, go for it.
At one point, I was going to take that out because maybe I don't want to do the slide where I talk about what your test is or something. And everyone that I talked to said, no, leave it the way it is, because those are more readable. It's cleaner and it's easier to read than like going to Catch or something.
Oh,
So
that's fantastic.
I think I'm leaving it in. I think I'm leaving all the examples in Boost UT for my talk.
Love it. Thanks for that. Appreciate it.
Yeah, it's a collab now.
Yeah, we'll have to mention your talk then. we can say that you can cheat unit testing. Ben may have ideas. I don't know how to plug you.
Interesting thought.
Well, we never thought about cheating unit testing.
Right, and I'm wondering also about jitting UDLs now.
Cheating UDL.
What that might mean. I wasn't sure. I was sort of thinking about that earlier.
Yeah, I know what that means. Like probably ICs.
So, Kris, is there anything in your project, like UT, that you haven't gotten to that you want to develop next? Or maybe you need some help and there's some people here that are interested in helping you on your project?
Oh, sure. If anyone wants to contribute, I'm more than happy. There are tons of features which Catch has, which are not implemented, like XML reporters and other things. It's by default it's like micro T, which is like light by default, and the idea is that UT is like with the guide of the C++ principles that you don't pay for what you don't use, but there are tons of features which could be implemented on top of it.
Cool. Do you have like a contributors page or something like that that says like the highest, I don't know, or just maybe a listing of those things, like you just mentioned your XML reporting or whatever?
No, I don't. I could add it though. That'll be a good idea.
Yeah.
Thanks for that. I will do that. And yeah, besides that, it's just GitHub. It's open source. You just fork it, put a merge request. Well, you test it, you add your test, and you merge request, and you're done. And I'll definitely take a look.
Awesome. It's always funny because there's some open source library maintainers that are open to that, some that are not. So I think it's good to at least communicate to the group here that you're open for that. So that's awesome.
Yeah, that's a verified point. I should state that everyone is welcome. I actually appreciate help always.
Cool.
If anyone is from Boost, I would also appreciate. Review managers are always welcome.
Cool.
If anyone is interested in fighting Bryce with the standardization, because he has strong opinions about that, it's also a thing.
You just need somebody with strong will, right?
You need a strong will. I feel like there are strong arguments on both sides.
Yeah.
But you know, like with the standardization, you have to have quite a bit of willpower to proceed
Yeah,
to the end.
for sure.